This video was inspired by a comment on my previous video about the 1907 Kingston earthquake. Brian Curtis, one of my regular viewers, asked whether earthquakes might be able to bring minerals close to the surface and whether there could be a potential silver lining, as he put it. That comment reminded me of a 2024 study published in the journal Nature Geoscience, where a group of Australian researchers proposed a fascinating link between quartz piezoelectricity and the formation of gold nuggets. So, can earthquakes actually contribute to the formation or concentration of gold? The short answer is yes, but not in the way you might think. Stick around to find out more. Before we go any further, I think it is important for those who may be new to geology to understand how we get gold in the first place. I covered this in a previous video on the origins of minerals, but I'll briefly go over it again here and keep things simple. Many sources will talk about the astrophysical origins of gold. They might say something like all gold originated billions of years ago in deep space during the explosion of massive stars or the collision of neutron stars. And while this is both fascinating and scientifically valid, I don't usually focus on that part of the story. That explanation tells us where the element came from, but it doesn't really help us understand how we find, explore for, and mine gold here on Earth. Instead, I prefer to focus on the geological concentration of gold, how it becomes concentrated in the Earth's crust, where it occurs, and why it occurs there. So broadly speaking, gold is found in two main types of deposits: hydrothermal deposits and placer deposits. So hydrothermal deposits form deep underground. Superheated mineral-rich water, often containing dissolved minerals, circulate through fractures and falls in the Earth's crust, dissolving and transporting tiny amounts of gold. As these fluids cool or experience changes in pressure or chemistry, the gold precipitates out of solution and is commonly deposited within quartz veins alongside other minerals. A major subtype of hydrothermal deposits is known as orogenic gold deposits. These form during mountain building events where tectonic plate collisions generate heat, pressure, and extensive fault networks that allow mineral-rich fluids to move through the crust. Many of the world's richest gold deposits formed in this way. The second major type is the placer deposit, or the placer deposit, which is the one most people are familiar with from movies and documentaries where people pan for gold in rivers. Over long periods of time, weathering and erosion break down gold-bearing rocks, releasing gold. Because gold is extremely dense and highly resistant to chemical breakdown, it is transported only short distances by rivers and streams before settling out and becoming concentrated in riverbanks as flakes, grains, and sometimes large nuggets. And that, in a very simple and general sense, is how the gold deposits we explore and mine for today were formed. So before we dive into the paper, it's important that we talk about a special property of the mineral quartz known as piezoelectricity. I've actually covered this topic twice on the channel, once in one of my earliest long-form videos and more recently in a YouTube short. To quickly summarize, piezoelectricity is the ability of certain solid materials to generate an electric charge when mechanical stress is applied to them. So quartz is one of the most well-known piezoelectric minerals on Earth. When it is compressed or deformed, it generates a small electric charge. This property has many applications, one of the most familiar being the quartz watch. In a quartz watch, a battery applies an electrical signal to a quartz crystal, causing it to vibrate at a very precise and stable frequency. And those vibrations are then used to regulate timekeeping with high accuracy. So up to this point, we've covered two key concepts. First, how gold deposits form, and second, the piezoelectrical properties of quartz. Understanding both of these ideas is essential because the 2024 Nature Geoscience paper brings them together in a very unexpected way, and that's what we'll explore next. As we've discussed, geologists have long understood how gold is transported through the Earth's crust. Hot, mineral-rich hydrothermal fluids circulate through fractures carrying dissolved gold. As conditions change, whether in temperature, pressure, or chemistry, some of that gold precipitates out, forming the quartz veins that host many of the world's richest deposits. But this system raises an interesting, long-standing question in economic geology. The fluids that transport gold are extremely dilute, often containing less than 1 part per million of dissolved gold. Yet, in many quartz veins, geologists find gold nuggets weighing kilograms and in some rare cases even hundreds of kilograms. Forming such large nuggets through simple precipitation from dilute fluids require either extremely large fluid volumes or highly efficient forcing of flow or additional enrichment processes operating over long periods. This has led researchers to explore what is sometimes referred to as the gold nugget problem. Now, the 2024 study published in Nature Geoscience proposes a possible contributing mechanism, and it begins with quartz and piezoelectricity. As we've discussed, quartz generates an electrical charge when it is mechanically stressed. During an earthquake, seismic waves compress and stress quartz crystals within fractures, producing small electrical charges. The researchers suggest that, in principle, these voltages may be sufficient to influence electrochemical reactions that can reduce dissolved gold from hydrothermal fluids, encouraging it to precipitate onto mineral surfaces within fractures, including quartz. Even more interestingly, once microscopic gold grains are present, they may locally influence how subsequent gold precipitates. Gold is a much better electrical conductor than quartz, so it can alter local electrical conditions at the mineral fluid interface. The researchers suggest that this could potentially encourage further gold deposition onto existing grains. To test this idea, the researchers mechanically deformed the quartz crystals while immersing them in gold-bearing solutions. They observed microscopic gold deposition on stressed quartz surfaces, while unstressed samples showed little to no deposition. When they use quartz that already contain gold grains, additional gold preferentially accumulates on those existing grains, consistent with the proposed mechanism. And it is important to note that laboratory experiments simplify the complexity of natural hydrothermal systems. However, they are useful for isolating potential physical and chemical mechanisms under controlled conditions. The authors propose that repeated earthquake activity over long geological timescales could contribute to the redistribution and concentration of gold within quartz vein systems, potentially helping to grow small gold particles into larger nuggets. Importantly, this does not replace the traditional hydrothermal model. Gold still needs to be transported into the system by hydrothermal fluids. Instead, This mechanism may help explain how gold becomes locally concentrated once it is already within quartz veins. If further studies confirm the importance of this process under natural geological conditions, it could represent a useful addition to our understanding of how gold may become concentrated in some ore systems. So, to sort of summarize everything, what the researchers are proposing is that earthquake-induced stress in quartz may generate electrical effects that could influence how gold precipitates within hydrothermal veins. Over time, repeated earthquake events may enhance conditions that favor further gold concentration, gradually enlarging small particles into larger nuggets. Of course, more research is needed to determine how significant this process is in natural systems, but it is a plausible and very intriguing hypothesis. So if you made it this far, thanks for watching, and I'll see you in the next one. Please take care.